So in this lesson, we're going to begin our coverage of linear Diophantine equations, which is going to be a recurring theme throughout the term. Now, before we get started, I want to return to an example that we were considering at the beginning of the previous lesson. So specifically, let's consider the set 2n plus 3m, where n and m are integers. We had a conjecture that s was equal to z. We can now prove this conjecture. Here's how. Let n be in z. If n is in z, then by Besou's lemma, there exists x and y in z such that 2x plus 2y is equal to 1, since the GCD of 2, that should be a 3. The GCD of 2 and 3 is 1. And actually, I'm going to change notation, since I already used n in the set notation above. Let's go ahead and call this r. So r is the integer. Now, if we multiply by r, we have that 2r times x plus 3r times y is equal to r. But by construction, this is an s. And so all we have done here is multiply this equation by the integer r. And since this is equal to 1, this is equal to r. And so now we have that we can take our n to be r times x, our m to be r times y, and we have the r is an s. And of course, if we chose an element in s, then that element is automatically going to be of the form 2n plus 3m. That's gonna sum up to an integer, so the converse is automatic. And then, so the converse is automatic. Since s is a subset of the integers. And so now we have shown that z is in s. So we now have the proof. So s is in fact equal to z, and this is now promoted from conjecture to, it's not big enough to be a theorem. So let's call it a lemma. So we have our statement, and as a consequence of this, we now have that the polynomial equation, the equation a is equal to 2x plus 3y has integer solutions for each integer a. And this is the foundation of what we're going to be looking at for linear Diophantine equations. So specifically, here's the definition that we will be using. So by a Diophantine equation, we're going to be looking at polynomial equations in two or more variables. We just considered variables x and y. But more generally, we have that it's just a polynomial equation, but we're looking at the integer solutions. And I'll come back to that in a moment by what we mean by only interested in integer solutions. We say that a Diophantine equation is linear if each of the variables appearing has degree 1. And so, for example, a linear linear Diophantine equation in n variables will have the following form: a1 x1, a2 x2, all the way to an xn, and that's equal to m. And we're assuming that all the coefficients a sub j are non-zero integers, and also that m is an integer. And so that's an instance of a Diophantine equation, and we have seen examples of this. The one thing that differentiates Diophantine equations from what we have seen in the past is the terminology of only focusing on integer solutions. So let's look at our example, 2x plus 3y equals to 1. So here we have it. We're back with 2x plus 3y. Now we're setting it equal to 1. We know from our construction that we can how to find those x and y's, Bezout's lemma, and then we can multiply by any integer. So going back to the previous example, we have that in this case, did not mean to erase. Here we have rx, comma ry is a solution, and we get back r. And so now we know that here we will have infinitely many possibilities for x, y based on our introductory example at the start. But here's the thing. When we're looking at the solution set of a Diophantine equation, we're only looking at the integer solutions. So yes, 1/2 comma 0 is a solution, because if we plug in 1/2, we're going to have 2 times 1/2 is 1, plus 3 times 0, so we just have 1 equals 1, so that's a solution. But it does not count because it's a rational number that is not an integer. And so that's out of the question. And so that's the one distinction. We are looking at polynomial equations, but only care about the integer solutions to said polynomial equations. For example, if we look at the unit circle, x squared plus y squared equals 1. It's a Diophantine equation. It's not linear because now we have x squared and y squared. And to be linear, we need all the variables appearing to have degree 1. So this is a non-linear Diophantine equation. But we could ask, what are the solutions to the Diophantine equation? Well, we have been accustomed to saying there's infinitely many, all the points on the circle, in the unit circle. But now, the restriction that the solutions have to be integers forces it to only be 4 possibilities. Plus or minus 1, 0, or 0, comma, plus or minus 1. And so that's another example. We can look at our favorite SAT questions. Let's look at the Pythagorean triples. We have our triangle, 3, 4, 5. That's a horrible looking 3. So here's 3. So this is a Pythagorean triple. It satisfies those 3 squared plus 4 squared equals 5 squared. It satisfies this equation, so that will be a solution to the Diophantine equation, x squared plus y squared equals to z squared. And in the homework, exercises 18 to 22 of 5.2, you will be investigating Pythagorean triples further. And one of the questions that we will be focusing on later in the term is the question, are there infinitely many Pythagorean triples? And I'll come back to that in just a moment. Going onwards, if we instead replace the 1 in, so if we look at the z squared, and now don't consider it as a z squared, but plugging in a constant. So Fermat's sums of squares theorem can be restated as a Diophantine equation. We can choose the prime to be p, and we can then say that the Diophantine equation x squared plus y squared equals p has a solution if and only if the prime, when we divide it by 4, has remainder 1. Because if we look at x squared plus y squared equals 3, we know that it is not possible to get an integer solution to that. And so in that case, the solution set would be empty. So solution set to x squared plus y squared equals to 3 is the empty set. And so in that case, we will have empty solution. Even though in the real numbers, this is solvable. And that's the key difference. Only care about integer solutions. Another example of a Diophantine equation is what is known as a binary quadratic form. And so these are Diophantine equations of the form ax squared plus bxy plus cy squared, where now a, b, c, and n are all integers. And one of the great things about this topic is that in studying the properties of such Diophantine equations, Lagrange in 1775 was able to devise a new proof to Fermat's sums of squares theorem, giving now, at that point in time, the second proof to the statement, since Euler discovered the first. And one of the beautiful aspects of mathematics is that in this situation, Lagrange was studying Diophantine equations, devised a new proof of Fermat's sums of squares theorem, but Gauss was able to go one step further and uncover marvelous aspects of these Diophantine equations that had deep ramifications throughout number theory. And one of the final projects for the course is actually going to investigate binary quadratic forms in more generality. And just notice that its connection to Fermat's sums of squares comes from the fact that if we take A to be 1, C to be 1, and B to be 0, and N to be P, then we are back in the setting of Fermat's sums of squares theorem. And so this is a topic that you can investigate further. And now we move to the elephant in the room in number theory, Fermat's last theorem. And what it says is, if we have an integer n greater than or equal to 3, all the solutions to the Diophantine equation x to the n plus y to the n equals z to the n, they all satisfy x times y times z is equal to 0. Because of course we can take 0 to the n plus 0 to the n equals 0 to the n. We have a solution. Or we can take 1 to the n plus 0 to the n, and that's equal to 1 to the n. Another solution. But they all satisfy that if we take the product of x, y, z, we get back 0. And so the story goes back to Fermat. A French lawyer, he had a copy of Diophantus Arithmetica. And he was motivated by a proposition in Diophantus Arithmetica regarding Pythagorean triples, which gave a way of finding all Pythagorean triples. And in the margin of his copy of Diophantus Arithmetica, Fermat wrote the following famous marginal note. It is impossible to separate a cube into 2 cubes, or a fourth power into 2 fourth powers, or in general, any power higher than the second into 2 like powers. I have discovered a marvelous proof of this, which this margin is too narrow to contain. And it left off a storm of amazing mathematics that has come from that statement, to the point where, as we will see in this course, Fermat's last theorem in many ways is single-handedly responsible for the achievements in algebra number theory that happened in the late 1700s and 1800s, since mathematicians were focused on proving this result. And even though they were not successful, they developed machinery and techniques that would lead to other discoveries. And even when it was finally proven in 1994, the techniques developed, specifically using the theory of elliptic curves, led to results in cryptography, to the point where now, in that branch of mathematics, on the quantum computing side, if a quantum computer does become a thing, a lot of our crypto systems become obsolete. And one of the major branches of research right now is developing crypto systems that are quantum safe. And so algorithms that are resistant to attacks from a quantum computer. And elliptic curves have posed a possible avenue for developing such algorithms. And so this is one instance where we have a statement, has nothing to do with any of these other things that were discovered, but in proving it, we develop those techniques. And we will see instances of that as we go through the course. As this will be a recurring theme for it. But let me just go ahead and just briefly discuss the history. Fermat is credited with proving the n equals 4 case. And we will actually see his proof in this course. And honestly, it's not really a great proof. He even ends the proof by saying, I have run out of space in this margin, so the argument then follows. And so doesn't really demonstrate his reasoning. But historically, it's still attributed to him. This was a marginal note from 1641. And in his copy of Diophantine Arithmetica, Fermat wrote 48 marginal notes. So he wrote 48 marginal notes. One of them, of course, was also the Fermat sums of squares theorem. And what happened is that Fermat was writing these notes for himself. It's not that he was purposely writing these notes with the intention of publication. So the n equals 4 note dates to 1641. Fermat's last theorem, this note dates to 1637. And so it was a book that he was coming back to throughout his life. When he passed in 1661, his son went through his copy of Diophantus Arithmetica and published a new version annotated with the notes that his father had written throughout his lifetime. Now, these notes were in Latin, so it was translated in French and republished. And at that point, Now we're talking 20 years after Fermat had said this claim. Fermat had gained a reputation in the mathematics community. He corresponded with mathematicians, including Mersenne. Newton came to know of him, and he also is credited with having discovered the difference quotient, the derivative that we use in calculus, the power rule. The derivative of x to the n is n times x to the n minus 1. He discovered the first instance of that as well as integration formulas. And so, while he's not a mathematician in the sense that he was not an academic, his day job was a lawyer, he was known in the mathematics community for what he had done through the correspondences with academic mathematicians. And so once his copy, the marginal notes were published in the publication that his son made, mathematicians bought the book, went through the marginal notes, and started working one marginal note at a time, and some were incorrect, and we'll see one of those instances later on. So not all the marginal notes were correct. The reason for the name last theorem is that of the 48 marginal notes, that was the last one to be established. And so let's look at the timeline. So 1637, the statement was originally written. Fermat, n equals 4 technically, in 1641. Euler discovered a new proof of this as well, which we will discuss in this course and prove. Euler did the n equals to 3 case in 1753. And Dirichlet and Legendre did it the n equals to 5 case in 1825. But between the original statement and then if we include the 4 in there, it took over 100 years to go from 4 to 3. And then another 70 years to go from 3 to 5. And it's not that Euler and no one between Fermat and Euler worked on this, is that this is an incredibly difficult question to attack. And the same thing with Euler going to Dirichlet and Legendre. It's not that they were the ones who, the only ones who worked on it and proved the result. Many mathematicians devoted their lives to working on this one statement. And the downside with these timelines is that we only see the victors, the ones who came at the end, and that leaves out a crucial development that happened in between 3 and 5, which without Dirichlet and Legendre would never have been able to prove the result. And that is the work of Sophie Germain in 1823. Prior to Germain's work, Fermat, 1 exponent 4. Euler, the exponent 3. Everyone else that had been attacking this problem was working 1 exponent at a time. Okay, we got 3 and 4, so let's work on 5. And then after we get 5, we'll work on 7. And we will see later that the 6 and the composites we don't really have to consider. We only have to look at the prime powers. And Sophie Germain had a different approach. She dared to question the way that mathematicians have been approaching it up to that point and said, if we just continue doing it 1 exponent at a time, we're never going to solve Fermat's claim. Yes, there are no techniques available to do them, so let's discover those techniques. And that's what Sophie Germain did. She established a program that will allow mathematicians to consider not just 5, 7, but just arbitrary exponents at a time. And she broke up Fermat's last theorem into 2 cases. The first case of Fermat's last theorem and the second case of Fermat's last theorem. And we will be proving at the end of this course Sophie Germain's theorem on Fermat's last theorem for the first case for what are known as auxiliary primes. And so that will be one of the last results we will show in this course. But as a consequence, by having broken Fermat's last theorem into case 1 and case 2, and having proven the result for case 1 for a good collection of exponents, Dirichlet and Legendre only had to work on the n equals to 5 case 2 part of Fermat's last theorem. And that's what they did. So when we say that Dirichlet and Legendre proved the n equals to 5 case, they proved the second case. But the first case is due to Germain. Now, unfortunately, that's not where the timeline ends for this problem. It goes on. So I'm just going to put in a couple of dates here. The n equals to 7 case was Lemay, whom we will talk about later. This was in 1839. And then in 1847, Ernst Kummer, whom we will talk about at the end, proved Fermat's last theorem for what are known as regular primes. And we'll talk about what it means to be regular towards the end of the course. And then finally, it was proven by Andrew Wiles in 1984. And so that was when it was finally settled. But even then, it's a bit of a understatement to say it was just Wiles. In 1981, a series of conjectures was given by Gerhard Frey that stated that if Fermat's last theorem is false, then something horrible will happen in the world of elliptic curves. And that led to a string of arguments that many mathematicians contributed, Sir, Rivet, many others, and Andrew Wiles was the one who finally proved the last string of the conjectures, which was at that time known as the Taniyama-Shimura conjecture. If you're interested in the history of the modern achievements of Fermat's last theorem, here's a link to Daily Motion. So shortly after the proof was completed in 94, BBC made a documentary of the proof of Fermat's last theorem, and I highly recommend watching this video, as it's a great documentary. And it's what got me into number theory, I would say. This Fermat's last theorem is a beautiful question with lots of history, but also a very useless problem. Why is it useless? Well, we have talked about the history. It took over 3 centuries to actually settle this claim that Fermat said to have proven. And actually, last thing on the historical side and rambling, what it has been established is Fermat wrote that note in 1637. Again, he never intended these marginal notes to be published. So when he wrote the note, he thought that he had a proof, but as is evident, 4 years later, by having done the n equals 4 case and written the proof in the margins, he realized at some point in time that his original argument was incorrect, and then resorted to only working on one exponent at a time. And so we also know from his writings that he struggled with the n equals to 3 case, which Euler would do over a century later. And so the consensus is he knew he did not have a proof, but he never went back and erased the note in the margin. And oftentimes that is left out from conversations of Fermat's last theorem, as it makes it seem that, yes, Fermat had a proof. No, he did not. And he knew it. Otherwise, he would not have done a proof for n equals 4 alone 4 years afterwards. And also in his correspondences with other mathematicians, he never made the claim of what we call Fermat's last theorem. Instead, he challenged mathematicians to prove the n equals 4 case and the n equals to 3 case, but never the general case, which is also indicative that he knew he did not have a proof. So now let's come back to seeing why Fermat's last theorem is useless from a practical point of view. And it has virtually no applications. As an example, here's a corollary that we can use using Fermat's last theorem, and that's essentially it. So while useless, that doesn't mean that it's a worthless problem, because the techniques required to prove it developed a lot of mathematics, some of which we will be focusing in this course. So let's apply it. Assume Fermat's last theorem. So we're going to assume Fermat's last theorem. And we're going to prove that the nth root of 2 is irrational for each integer n greater than or equal to 3. So towards a contradiction, let's suppose that the nth root of 2 is rational. Then there are integers a and b with the GCD. We can always get this in simplified form. GCD of a and b, so a and b are relatively prime, such that the nth root of 2 is equal to a over b. Now, let's take nth powers on both sides. So now we have 2 is equal to a to the n over b to the n. which then tells us that then we have 2 times b to the n, which is the same as saying b to the n plus b to the n equals a to the n. Now, n root of 2 is a real number, it's non-zero. So what we have is a solution. We have then that b, comma a is a solution to the Diophantine equation. X to the n plus y to the n equals z to the n. But ab squared, a times b, is non-zero. So n must be equal to 2. Well, we're not gonna, the first root of 2 would just be 2. 1 over that. So n must be 2. And so what we have there is, if n is greater than or equal to 3, we just have a contradiction, since we do assume that n is at least 3. So that's the assumption, so we have now a contradiction. Since n is greater than or equal to 3, and so we are done. And so we have our proof. And that is the essentially only application of Fermat's last theorem, one of the only applications of Fermat's last theorem directly. And it's overkill because then it begs the question, in the proof itself, is this statement ever used? Because if at any point that assumption is there, then it really isn't a consequence, because it's assuming it's a circular argument by having assumed something that is used along the way. And so that's Fermat's last theorem. We're going to be talking about it in great detail in this course, and so that's going to be a recurring theme for the very purpose that number theory has arisen from the work that has gone into proving this statement. On a similar note, we can try to generalize Fermat's last theorem and look at the equation x to the 4 plus y to the 4 plus z to the 4 equals w to the 4. So just add an extra term. And Euler considered this in 1750. And he believed that, just as with Fermat's last theorem, that if a solution existed to this Diophantine equation, it must satisfy that x, y, z, w, the product of it, must be 0. And this went unanswered for a good chunk of time until 1988, when it was finally shown by Noam Elkies to be false. And Elkies found the following counterexample. The smallest solution is this one. And Elkies went actually one step further. He showed that not only is it false, but there's infinitely many solutions that don't satisfy that. And those solutions also being relatively prime. Because once you have this, you can also cheat, because you can also take any number, multiply it over. So if we take some n to the 4th and multiply it to each side, we technically can have infinitely many solutions by putting a n to the 4 over here for any integer. So once you have a solution, you technically have infinitely many. But Elkies did account for that and show that there's infinitely many solutions where each of the quantities are relatively prime to avoid cheating in that fashion. Alright, so now that we have set the history, the tone, and brought up some questions that we're going to be focusing throughout the term, let's go ahead and prove some things building on where we left off last time with Bezout's lemma. So we are going to now show the following statement. If a, b, and n are integers, and we know that at least one of a or b is non-zero, then the Diophantine equation ax plus by equals n, it has a solution if and only if the GCD of a comma b divides n. So let's go through this. So let's do the converse first. The converse is quite nice and automatic. So for the converse, suppose that the GCD of a comma b divides n. And actually, so that we don't have to write the GCD over and over again, let me just go ahead and impose from the start, let D be the GCD of a comma b. So the converse, so assume that D divides N. By Bezout's lemma, we have that there exists x and y in the integers such that a x plus by is equal to D. Now, we're going to do the following. Since D divides N, by definition, there exists some u in Z such that N is equal to u times D. So if we multiply now the equation ax plus by equals D by u, then we have a times ux plus b uy is equal to u d, which is equal to n. But now this implies that the element ux comma uy is a solution to the Diophantine equation. Equal to n. And so we have, by Bezout's lemma, that the converse holds. And so now we have shown that there is a solution. Also, a quick comment. In number theory, it's common to leave the capital letters x and y and z, as we have seen in this lesson, for variables. Whereas the lowercase letters, in this case, the lowercase x, the lowercase y, those we're taking them to be integers. And so whenever I'm working with variables, you'll see that I'm going to be using capital letters for them. And so just something to mention, since oftentimes calculus, linear algebra, we're used to seeing lowercase x or lowercase y as a variable. Here, the lowercase x and y will usually refer to an integer. So now, this is the forward direction. So this one's also not so bad. For the forward direction, we're just going to assume, suppose ax plus by equals n has a solution. Well, let's go ahead and call that solution u and v. So u comma v, and these are both integers, so I'm going to put this as a Cartesian product of two copies of z. Suppose u comma v is a solution to ax plus by equals to n. So that means that then we just have au plus bv equals to n. And what do we have at our disposal now? We know that D is the GCD of A and B, so D divides A and D divides B, so linear combination lemma to the rescue. So by the linear combination lemma, we have that D divides N. And that's what we wanted to show. And so now we're done with the proof of this theorem. And so whenever we have a Diophantine equation, we have a classification for when we have a solution to this equation. So as a corollary, we have that if we were to look at the solution set of 3x plus 9y is equal to 2 is the empty set. Because 3 and 9, the GCD, is 3. And the only way we can have a solution is if 2 were to divide, if the GCD of 3 and 9 divided 2, which is definitely not the case in here because 3 does not divide 2, so it follows that the solution set is empty. Alright, so now we come to one of the cornerstone results in elementary number theory. And actually, that reminds me, I meant to make a comment about this. The title of this course is The Elementary Theory of Numbers. Why are we using the word elementary? Because a lot of these things are not as elementary in that sense that they're just going to be automatic or like easy to prove. As we will see, we're going to be covering some quite difficult arguments, but we will conquer them. The reason for the word elementary is that in modern number theory, it has branched out. Elementary number theory refers to number theory that can be done without adherence to the modern branches of mathematics. So what I mean by this is the results that we will cover in this course do not rely on techniques done in abstract algebra or in real analysis. This coming spring, Caroline will be teaching a course in analytic number theory. It doesn't have the word elementary because it's now assuming techniques in analysis, and therefore that word elementary is just reserved to things that don't require any additional mathematics past the 1800s. And usually around 1850 is where the line is drawn. Anything prior to the 1850s is usually considered elementary number theory, with a couple of exceptions. There are some results in analytic number theory that date before 1850s, but usually early 1800s. And so that's just something I want to point out as to where this word elementary is coming from. It's just a reference to not using higher level mathematics courses. We won't be using techniques from topology, analysis, algebra, which modern number theory uses. In many ways, I like to consider modern number theory as, like, for us in the work in number theory, we are the applied mathematicians of theoretical mathematics, because we go into every branch of mathematics and we get what we need to prove results about the integers. And so that's just a little side note as to where that word comes from. Alright, so let's get started and now prove Euclid's lemma, which is actually going to be the key result we need to prove the fundamental theorem of arithmetic in the next lesson. The statement that the textbook calls Euclid's lemma, and I've resorted to following the textbook, is the statement here, but that's not what Euclid's lemma originally was. This is a generalization due to John Prestet. And after this, we will actually have as a corollary the original Euclid's lemma. But let's go ahead and prove this statement. So what it says is d, m, and n are integers. If d divides m times n, and d and m are relatively prime, then d divides n. So let's prove it. So for the proof, let's use the fact that the GCD of d and m is equal to 1. Then Besu's lemma implies that there exists x and y in the integers such that we have that d times x plus m times y is equal to 1. Okay, so we use the assumption that the GCD of d and m is equal to 1, but how do we tie this in? Well, here's the key observation. We know that d divides mn. That's our second assumption. We see that m is here. There is no n in this equation, so let's multiply by n. So multiplying by n yields that the equation dxn plus mny is equal to n. And so now we have this here. And now we have to use the following property, that d is here, so d divides d times xn automatically. But the assumption is that d divides m times n. So d divides this. So now the linear combination lemma once again comes to the rescue, because it now tells us that d, since d divides this and this, it must divide n. Oops, wrong thing. So by linear combination lemma, d divides n, which is what we wanted to prove, and so we are done. We have the proof. And now we get to what is referred to the original Euclid's lemma. And what it says is, if p is a prime number, and a and b are integers, if p divides ab, then P divides A, or P divides B. Why do we get this automatically from Euclid's lemma? Well, in lemma 1.4.3, we can take D to be P, and M to be A, N to be B. And so we know that in this case, we have the assumption that D and M are relatively prime. So the way we go about this is towards a contradiction. Suppose, by way of contradiction, that P does not divide A, and P does not divide B. Well, if this is assumed, now lemma 1.4.3 applies, since we have that second aspect of the GCD of D and M. And so now by lemma 1.4.3, we have that P divides B. So B, B I took to be N. So P divides B, since we're assuming, since we have that the GCD of A and P is equal to 1 by our contradiction assumption, and then we're using that in our statement from Euclid's lemma. And so we have P divides Mn, that's our assumption, P divides AB, and so we're done. And so this is a contradiction. Contradiction. Let me close that parentheses there. That P divides B, but P does not divide B, so we are done. And we have proven the original Euclid's lemma. So for the homework, you will be actually generalizing the original Euclid's lemma in this statement, which is corollary 613 in the textbook. And what it says is, if P is a prime number that divides, P is a prime number, and then we have A1 through AR integers, such that P divides the product of A1, A2 to AR, then P must divide one of those A sub j's. And so we just looked, in the case of the original Euclid's lemma, that's the case when j is equal to 2. And so you'll be proving this for homework as part of exercise number 7 in section 6.1. So before we move on, I want to just make a final comment on Euclid's lemma. So we have given a modern proof of it because we rely on Bezo's lemma, which dates to 1624, and of course Euclid was 300 before the Common Era, so how did Euclid prove it? He didn't have these techniques. So in the lecture notes, I have at the end of the section 4, in the lecture notes, there is a proof that goes over the argument using the well-ordering principle. But the proof is very reminiscent of the movie Inception, in that it has multiple layers. You actually have to use the well-ordering principle twice in a very clever way to get the argument. And so Bezo's lemma saves us so much work, but as you go through the proof, you will see that there's a lot of similarities. And I will also be posting a video I recorded last year that goes through that same proof, but it's a longer video, and so that's optional. So that's just something as an aside, since that is one of the main ingredients for proving the fundamental theorem of arithmetic, and because we use Bezo's lemma, technically that's not the same argument that Euclid used. And so if you want to see the arguments leading up to that proof, they're available in the lecture notes and in the additional video that I will be uploading. So now we have come to the classification result of this lesson, which will allow us to deduce what is the solution set to any linear Diophantine equation. And so here's how it works. We start off with relatively prime integers, a and b. We know by Bezo's lemma, and the results that followed it, that we can find a solution x comma y satisfying this equation. So we know that there's at least one solution to it. Then what the theorem asserts is that the solution set to the Diophantine equation is exactly the set S, where we have the x and y that we start off assuming our assumed solution, and then it's just x minus kb, comma y plus ka as k ranges over all the integers. And so we're going to go ahead and prove this, and it will be a demonstration of how Euclid's lemma is utilized. So what is the strategy for this? So here's how we're going to do, what we're going to do for this proof. So the strategy is to do a double set inclusion. So what we are going to do first is suppose that x comma y is in the set S. We're going to show that then this implies that that this is x comma y is a solution. X comma y is a solution to the Diophantine equation. So that's one approach. The second approach is to pick any solution. So let capital X comma y be any solution, integer solution to the Diophantine equation. A solution to the Diophantine equation. And then we're going to show that that solution is in S. And so that's our approach. We start by choosing something in S, showing that it's a solution. Then we start by choosing a solution and showing that that's in S. And that will give us what we want to prove, that the set S is exactly the set of solutions. So how do we prove this? So let's do the first case first. So we're going to go ahead and suppose that, so I'm going to be careful and not use capital X and Y as I use in the setup. But let's go ahead and suppose that U comma V is an S. Then that means that there exists a K in the integers such that X minus KB is equal to U and Y plus Ka is equal to V. And so that's what we have. So now let's plug that into the Diophantine equation. We're going to plug in and see if we get back in. So we plug in, and so now we have A, X minus KB. So we plugged in U for X. And then we're going to do plus B, and then plug in V for capital Y. Now let's expand. We have AX minus AKB plus BY plus BKA, which I'm just going to write as AKB using commutativity. So what we end up getting now is cancellation. The AKB cancels off with that negative, so that's gone. And so we're just left with AX plus BY. But the assumption is that x comma y is a solution to the Diophantine equation, so this here is just n by assumption. And so now this tells us that u comma v is a solution. To ax plus by. So we have done the easy part, so we're now done with that part. So let's go ahead and move on towards the second case. Alright, so let's go ahead and do the second case. So I'm going to start over here since we're going to need a bit of space for this one. So we need to start by assuming a solution, and we want to show that that solution is an S. So let's go ahead and suppose that x prime comma y prime is a solution to ax plus b capital Y equals n. So in other words, we have ax prime plus by prime is equal to n. That's our assumption. We also have that that ax plus by is equal to n. So subtracting the equations, come over here. So we're going to subtract these two equations from here. And so I'm going to subtract ax plus by from this equation. And so that will give us, after subtracting and collecting like terms, we'll have a, since we have a common factor, and it'll be x prime minus x. And then we're going to have a plus b, y prime minus y. But then we have n minus n, so that will be 0. And let me just separate this here. Give me one moment. Okay, so let's go ahead. We're going to proceed by cases. So case 1. We're going to suppose that a is equal to 0. But if this is the case, since the GCD of a and b, they are relatively prime by assumption, so this is equal to 1, we have that b must be equal to plus or minus 1. So that's going to automatically force some structure on what b is. Next, we see that from the subtraction that we have here, we have that b, y prime minus y, is equal to 0. Then the zero theorem tells us that b, or y prime minus y, is equal to 0. But we know that b is plus or minus 1. So now that means that y prime equals y, since y prime minus y is equal to 0. So we have this here. Since b is equal to plus or minus 1, and x prime is arbitrary, actually, let's not use the word arbitrary here. We can find, since b prime is equal to plus or minus 1, we can find an integer k such that x prime is equal to x minus kb. And so we have this here. So remember, we're just taking k to be b to be plus or minus 1. So we just have to go ahead and find the right value to subtract off kb to get down to k prime, to x prime. So here we're using crucially that b is equal to plus or minus 1. So we have x prime written in this way. So now, the next thing, we know y prime is equal to y. And so now we want to show that y plus ka is also a solution. But what is a? A is 0. And so we are done. So we have that x prime comma y prime is the same as x minus kb comma y, which is an s. Because in here we have that a is equal to 0, so we're done with this case. So now let's go ahead and move on towards the case when a is non-zero. So now we come back to this equation up here, star. So if a is non-zero, by star, we have that b y prime minus y, let me write this as a negative right there, is equal to a x prime minus x. So in other words, a is a factor. So a divides b y prime minus y. And now we go to Euclid's lemma. Here we have, in this situation, D is taking the row of A, and M and N are taking the row of B. M is B, and N is y prime minus y. And so here we have that because A and B are relatively prime, Euclid's lemma implies that A divides y prime minus y. So there exists some integer k in Z, so k in Z such that ak is equal to y prime minus y. And so here we have our statement. So now what we are going to do is go back to the equation star and substitute this in. And so doing so now star is the same as a x prime minus x plus b times y prime minus y, which is now ak, equals 0. So we have this here. And so now, if we factor out an a, we have x prime minus x plus bk is equal to 0. But the zero theorem tells us now that x prime minus x plus bk must be 0. So x prime minus x plus bk must be 0. So I'll get some more space. So now we are essentially done, because what we have just shown is that going from this equation, we have x prime is equal to x minus bk. And so we have this here. But if we come back to this equation here, we also have, so we have x prime is equal to that, and y prime is equal to y plus ak. And as a consequence, we are done, since now x prime comma y prime are in S, since that's exactly what we wanted to show. X prime is equal to x minus kb, and y prime is equal to y plus ka. And so this finishes off this argument. And so we are done, and now we exactly know what is the solution set to any linear Diophantine equation. So let's go ahead and work out an example. So here we have 35x plus 15y equals 5, and we have already seen via Blankenship's method that 1 comma negative 2 is a solution to this Diophantine equation. And now we want to find the solution set to this Diophantine equation, but we can't apply the theorem just yet. In the theorem that we just proved, we assume that a and b are relatively prime integers. 35 and 15 are not relatively prime. But we can go ahead and overcome that by the following lemma, which is an easy observation here. So the statement is as follows. Let a and b be relatively prime. Then u comma v is a solution to ax plus by equals 1 if and only if u comma v is a solution to a n x plus b y bny equals n for any integer n. So this is really just an automatic statement. So we can observe that if u and v is a solution, then we have AU. So the forward direction, we assume UV is a solution. So AU plus VV is equal to 1. We multiply by n, and we have A and U plus V and V equals to n. And then the whole process is reversible because we can just divide. If U is a solution to this Diophantine equation here, then we can always divide off by n to return back to this and conclude that. So we have that. So with that in mind, even though at first glance the solution set to 35x plus 15y equals 5 doesn't seem to be attained from the theorem, it's perfectly fine because the theorem tells us this lemma tells us if we reduce this to the case where A and B are relatively prime, we get our answer. So let's go ahead and do that. So I'm going to put it here, a bar. So now 1 comma negative 2 is a solution to 35x plus 15y, but it's also a solution once we divide by 5. So we have 7x plus 3y equals to 1. By the theorem, (1.4.6), the solution set to 7x plus 3y equals 1 is the same as the set. So here 1 is x, so we have 1 minus kb, where b here is 3, comma y, which in this case is minus 2, plus ka, which in this case is 7, where k is an integer. And then by the lemma that we just saw, S is the solution set to 35x plus 15y equals to 5. So whenever you're finding solution sets to Diophantine equations where you don't, linear Diophantine equations where you don't have the A and B being necessarily relatively prime, divide off by the GCD and then apply the theorem to that corresponding equation and you'll get your result. Alright, so let's go and consider another example. Here we have 35x plus 15y, but now it's equal to 20. And we want to find the solution set. So if we take the GCD, this is different than the last example to some degree, but not so much. So we have 35 and 15. This, of course, is going to be 5. So if we divide that equation by 5, we get back divide by 5. We will get 7x plus 3y, but now it's equal to 4. So here's where we have to now be careful. Not much, but just a tiny bit. Because the lemma, I wrote it off in terms of that being equal to a 1. Whereas now it's equal to 4. So does that change things much? And the answer is no. Because if we go through this lemma and we just replace everything. So here I'm going to change the 1. And now let's go ahead and say that this was equal to m. So now when we multiply out, this will be n times m. And then when we have done the proof, this would have been m. Multiply this out, we would have gotten that this here, the only difference is that now this will be n times m. And so the proof will still hold. I just chose 1 because it was the simplest case, it was relatively prime. But in this situation, we have A and B are relatively prime. So Bezout's lemma tells us that, not Bezout's lemma, but the result that we showed after Bezout's lemma, that if they are relatively prime, then we will always be able to find solutions over here. And so that's the only thing that changes. They're relatively prime, but we know that we can always find a solution to this equation because a linear Diophantine equation has solutions if and only if the GCD of A and B divides n. Since they're relatively prime, 1 divides n, always, so we're good. And so, just as with this example that we just did here, all we have to do is then you apply the theorem to find the solution set of this, which in this case, well, first off, we need a solution. In this case, we can eyeball it and see that the solution 1 comma negative 1 is a solution. So the set of solutions that we want is going to be 1 is x in this case, minus kb, so 3k, comma, y, which is negative 1, plus ak, and in this case a is 7, so we have 7k, and then k is an integer, so we have this solution set here. And so by the modified lemma now, S is the solution set to this here. And so we are now done with this example. So now I want to come back to the same example and make a comment, because there's going to be questions where we cannot just eyeball a solution. And that was one of the negative things about the previous example. The way I went about it was by saying, oh, 1 negative 1 is a solution. So let's suppose that we're trying to find a solution set to this equation. And let's just work out the details. We divide out by 5 like we did. We get 7x plus 3y equals 4. But let's not assume that we can eyeball it. How do we find a solution to that Diophantine equation? Blankenship's method tells us a solution, but when we have the Diophantine equation equal to the GCD of the coefficients. So specifically, instead of looking at 7x plus 3y equals 4, Blankenship will tell us a solution to 7u plus 3v equals to 1. And in this case, if we apply Blankenship, which I have done down here, we will see that the solution is 1 comma negative 2, and so that's a solution to this here. But now, what we are going to do is instead make the following observation. If we multiply this equation by 4, we will get 7 times 4u plus 3 times 4v equals to 4. So that means that a solution to this equation is just a multiple of 4 from a solution for when it's equal to 1. So now, what we can go ahead and do is see that then the solution, this tells us that then 4 comma negative 8 is a solution to 7x plus 3y equals to 4. And so that's all we have done now, is we finally found a solution to the Diophantine equation here by first going to when it's equal to the GCD, applying Blankenship, getting a solution, and then doing this trick here. So we have 4 comma negative 8. Now the theorem tells us that the set S is going to be, in this case, x is 4. So we have minus kb. K in this case is still 3. So we have 3k. And then A is now y is in this case minus 8. And then we have plus ka, where we have 7k. K is an integer. And so we have this. But at first glance, these two sets look different. We have a 4, here we had a 1. Here's a minus 8, here we had a negative 1. But now, observe that if we go ahead and plug in 1 minus 3 times negative 1, this will give us 1 plus 3, so 4. And the same situation will give us minus 1 plus 7 times minus 1, which is equal to negative 8. So we can actually show that this set here is exactly the same as this one here. And so this is just to show a way of doing it when we can't eyeball a solution but have to resort to Blankenship. So now I'm going to finish off with a corollary, which is just putting symbols in the argument that we just did below for the statement over here using Blankenship. And so I'm going to go ahead and just convince you of where things are coming from, and like this is really giving us abstractly what we just did. But the main thing is, if we understand how to use the theorem via the techniques used here, we don't really need this corollary, but we can generalize by putting everything symbolically to get it. And in the lecture notes, I encourage you to look at the proof, and you'll see that it's the same argument, just putting symbols in the computational argument we just gave. So let's see how what all these symbols means. So we're looking at the Diophantine equation, ax plus by equals n. In our case, we're going to be looking at the same Diophantine equation we just saw, 35x plus 15y equals 20. So we're going to look at the GCD of a and b. So we know that this here is 35 and 15, so that's going to equal 5. So that's equal to 5. Then we're going to write n, which in our case is 20, as 5, so m times d. And so in other words, here we have 4 times 5, so m is equal to 4. Next thing is to write a, 35, as a prime d. So this tells us that then a prime in this notation is 7. And then similarly, b is 15. We're going to write this as b prime d. So this tells us then that b prime is equal to 3. And so we have all the notation that this corollary is getting at. And with the corollary saying, once we have this notation, the solution set is exactly this set, where x comma y is a solution to ax plus by equals d. So we want a solution x comma y to 35x plus 15y equals 5. But if we divide by 5, we know that in this situation, we will have that 1 comma negative 2 is a solution. So we can take 1 comma negative 2. And so now the solution set is going to be mx. And so m here is 4 times 1 minus kb prime. B prime is 3, so 3k. My, m here is 4, so then times y, which is negative 2. And then plus ka prime, which is 7k. Plus 7k, k is in z. Oops, and I forgot, I just realized that. Typo there. And so we have our set, which is exactly what we just saw in the previous example. But again, this corollary is exactly that example, but putting symbols everywhere to get it. And so that concludes it for this lesson. And so we have gotten everything we need to now prove the fundamental theorem of arithmetic, which is the next lesson. And so we will then establish exactly what Euclid proved, that every natural number can be written uniquely as a product of primes up to order.